Alright, contestants, are you ready?
So ready!
Oh, great.
Ready.
I'm ready.
That's what I thought you all said.
It's going to go easy on you. We are going to learn about the life cycle of data.
What?
The life cycle of data.
Seriously?
In the DWeb.
Ah, that's so good!
I want to get my stones down. Megahertz at the back will heckle me.
Yo.
So the goal of this session is to understand how IPFS manages data. So I run a weekly video call for IPFS, and the thing that comes up most often is people coming to that call being like, I put some blocks in IPFS and then the network didn't magically store them for me. There's a lot of misconceptions about IPFS being some kind of cloud service. So I suspect that isn't the case with all of you here, but it's worth clarifying where the data is in IPFS. What makes it verifiable, and in what way is it P2P? So you've already done core course A by this point. So that was adding files, so that was DAGs, blocks, chunkers, that kind of thing. We're covering what happens after that. Hello.
Great.
Your radio show.
There was a lot of information yesterday. For the purposes of this course, all you need to remember is a file you add to IPFS is stored as blocks in your repo. So I am in charge of the IPFS web UI. I try and make it look better every day. My usual approach to problem solving is let's build a web app. So when I was tasked with this course, I just wanted to get like a visual understanding of what adding a file and it becoming blocks in my repo looked like. So this is a simple web app that just, you drop a file on it. You probably saw a similar one in Core Course A. So that one was showing you the DAG structure. This one is showing you what's going on in the block store. So this is a almost empty IPFS block store. There are some metadata in there. This is the pin set metadata. We'll cover that later. But just so that we're all on the same page visually, if I was to drop a file on this thing, pictures. So if I was to drop an image, our preferred cat image, you'll note he's also here. There's a connection. We'll come back to him later. If I drop my cool cat picture into my repo, it gets added as blocks. It's chunked up. You can change the chunk size, which would affect how many blocks that image became. And you can see there's some green ones, there's some red ones. This will have meaning, but just quickly, this is your root CID for that file. And there's a bunch of other blocks. We're going to go into this more later. I just want to get us all on the same page. Blocks in a repo. So, we're going to cover providing, or how you tell the IPFS network, I have these blocks, and how we use Kademlia to tell peers about which blocks that we can provide. We're going to cover getting, so IPFS get, or how you say in IPFS, I want those blocks. We'll talk about want lists, we'll talk about Bitswap, we'll talk about verified data and Bitswap sessions. And we're going to cover pinning. So that's how you tell IPFS which blocks to keep on your machine. And that means that we're going to talk about pin types in the pin set and garbage collection. And we're also going to cover do not want. We're going to cover deleting blocks, because sometimes you just don't want all of them. So how to remove blocks from your machine. And then also some thinking about in the future how we might share lists of bad bits that we want to make communal and well known. So, providing, or how you tell IPFS, I have these blocks. How do you inform the network of what you have? So first up, this should all be understood now, but to make sure that we're on the same page, we need to agree on how we name things. In IPFS, each block has a CID, which is the content address of the data. The name of the block is derived from the bytes it contains. Every unique block has a unique CID. So, in this way, CIDs are giving us a scheme for distributed naming. The steps for creating a CID allow multiple users to agree on names for blocks without asking a central authority. So peers who've never met can come up with the same name for an identical chunk of data without being told or without having to ask each other. this is very useful, which means we can move away from URLs. Like, content addressing lets us separate what we want from where we get it, and if we can remove an explicit location, and instead we can use the address to verify the data that we got was what we expected, well, this allows us to get the data from anywhere, which unlocks things like distributed co-hosting of data, which is like, that's for me like the most exciting thing about IPFS. Like being able to say like, I care about this data, I'm going to participate in hosting it, is an interesting radical improvement to the internet. But the data is still stored somewhere, and so how do we let the network know what content we're providing? So the challenge is, how do we locate content address data? Kademlia! In the short, this is how IPFS does it, and particularly this is the libp2p flavor of Kademlia, which has some mild changes, but nothing that we need to worry about for the consequences of this course. So if CIDs give us a scheme for distributed naming, Kademlia is providing a scheme for distributed discovery for finding content address data. So the Kademlia algorithm defines who to tell and who to ask about where to find data over a changing network of peers. So IPFS uses Kademlia to store records, like this one, about which peers are storing which blocks. So in a trivial centralized system, we could perhaps store these as like one big table that would let us look up, for a given CID, tell me all the peer IDs that are providing it. But it wouldn't scale to have every peer store information about every block that everyone has. So Kademlia teaches us how to distribute that table. So, just to get us all on the same page with definitions, Kademlia is a distributed hash table. So a table where the keys are hashes, or in our case, CIDs, is known as a hash table. A distributed hash table or DHT, gives us a way to split that table across all the peers. So the mental image is lots of small tables instead of one big table. So that brings us to the Kademlia's one weird trick. If we're going to split the table up, we need to know which peers to tell and which to ask, a subset of them instead of all of them. And Kademlia says, tell the peers with peer IDs that are most similar to the CID of the block that you have, that you can provide it. So they don't store it for you, they will store a record that says, I can provide this. So you might tell Brian that you can store bread. These are obviously fictionalized CIDs. You might tell Chandra that you can store cheese. This is obviously a grotesque simplification for anyone who's looked into DHTs and has implemented them, but it's a useful mental model to have if you haven't. And also to deal with peers coming and going from the network, the Kademlia algorithm suggests you tell more than one. By default, we tell 20, and in IPFS, we're looking at maybe increasing that number because the size of the DHT has exploded pretty massively recently. So there are lots of options for configuration, but the high-level principle is you tell peers whose peer IDs are most similar to the CID that you have, that you can provide it. Also, if content gets popular in the network, then multiple peers will be able to provide that same block. So you might tell QM Chandra that you can provide QM cheese by sending them this add provider message. And then another peer, QM Trillion, also has that block. So they too tell QM Chandra, I can provide this block. So now we have more than one peer telling another that they can provide it. So with this one weird trick, both parties know who to tell and who to ask about where to find provider records, who can provide this, without asking a central registry. It's a mechanism of like finding agreement in the unknown.
So this for one key, there could be multiple values.
Absolutely, yeah. So with a distributed hash table, it's key to value, and the value can be anything. And so for when you're telling a distributed hash table about providers, in our case, it's key to a list of peer IDs. Yeah. But so a peer ID doesn't help you discover how to connect to them. That's the first mapping. Then in libp2p, there's also a peer store that has the addresses, the multi-adders. So if I know a peer ID, I can go to the peer store and say, oh, I'm going to need to tell you about how to connect to this person, so I send you the multi-adders back. Also of note, this is a big simplification, like things like how similar a peer ID is to a CID is defined mathematically as the exclusive OR distance between the bytes that make up the peer ID and the bytes that make up the CID. We don't need to go into that too much now, and hopefully you covered it a little more in some of the poster sessions and some of the other courses, but it's a useful mental model to have, and it's good to know, for our purposes, it's useful to know that Kademlia is a mechanism that IPFS uses to enable peer-to-peer discovery of content. If I go and tell someone else on the network I can provide this CID, then that state is now outside of my control. Like, I, Zaphod, told Chandra I can provide cheese, but then I close my laptop and I drop off the network. There's no way for me to have told Chandra I can't provide it anymore, so Chandra now has some stale information about a provider. So we have this notion of re-providing that says every 12 hours at least you have to re-announce CIDs that you can provide so that the people hosting these records, these provider records for you, can tell the information is still fresh. So if they don't hear back from you 12 hours later, they're going to purge that record. Also, you can control which CIDs that you announce. As we saw in the quick visualization at the start, there are loads of blocks in your repo, some of them pinned, some of them are unpinned. You don't have to announce every single block you have, and there's a thing called a provider strategy that lets you change which blocks in your repo you can provide. So all is the default option, and then there are other options like roots and pins. We don't have to go too deep to that, but you can see these if you want to take this back to something concrete that you can look at yourself. If you have a look in your config file in your IPFS repo and look under the reprovider section, you'll see an interval. So that's to do with how often I'll reprovide, how often will I announce to the network I still have this thing. So keeping the provider records up to date more frequently. But 12 hours is the default, and there's no great reason to change that. And the strategy is set to all by default, and you can customize that to say just announce things that I pin, and we're going to go into pinning later, so that'll make more sense when we get to that. Also, you can see, yeah, question?
You would then need encryption, right, to prevent people from knowing exactly what content that you're storing, because otherwise the DHT kind of doxes you with what content that you have.
Yeah. You would. If you wanted this to be fully private, you would need that. And that doesn't exist yet.
Right. So then you would say for the strategy, you could do something that's more restrictive.
Yeah.
The way you use encryption.
Yeah. Right, so exactly. So the strategy right now, the only available strategies are fairly simple in just terms of scoping which blocks you will announce.
Right.
But there's no reason why you couldn't have a smart strategy that was like, please encrypt every block you announce, or I deem these to be public, only announce those.
Okay.
There's also bizarre as the onion transport for LibQB, so you can sort of have like Tor mask you as you move to the network.
Okay.
So when people find you, they find you as like a Tor.
Right. Wouldn't that also pollute the DHT, because there'll be a lot of just nodes joining temporarily, right?
We can talk about after, but it depends on how stable your circuit is, right?
Mm-hmm.
It can be a stable path to find you.
Okay.
Cool. Any other questions? All right. So to see this in action, it's all a bit theoretical at this point. You can run the command IPFS DHT find provs. You pass it a CID, and it will output a list of peer IDs that can provide that block. So under the hood, what has happened is you have looked for, in the closest peers that you know about, so the CID you provided, you have a list of connected peers and a list of peers that your DHT implementation knows about. And it's going to try and find the one that it deems most similar to the CID and ask them, do you know anyone closer to this, or do you have a provider record for this block, this CID? And so you'll either get a response, you'll either get a response that is, I can tell you who can provide this, or you'll get a response that says, I don't know who can provide this, but I do know about this other peer, whose I deem their peer ID to be more similar to the CID than mine. So you could go on a multi-hop journey to find the closest peer in the network And ideally, if things are working and someone can provide that, you converge on the same set of peer IDs as where to look for provider records. So this command isn't actually getting the blocks, it's just doing a DHT walk to find a list of providers for a given CID. Which gets us to getting IPFS get. What happens when you run IPFS get? So this is how you say to IPFS, I want those blocks. So we just learned how you discover which peers are providing, but how do you actually get the data? It's Bitswap. Bitswap is how you get the data. So this is the trading blocks with friends module in IPFS world. Bitswap has 2 jobs: to request blocks you need from connected peers, and to send blocks you have from peers who want them. So one important thing is like the libp2p implementation of Kademlia is a separate system from Bitswap, which is what trades blocks. So Kademlia is like peer discovery, who has the things. Bitswap is for your currently connected swarm, I can trade data with them.
And now for something completely different.
Right. So we've all sat down and listened to me talk for a little bit, and so now it's time for some dance. A small dance that will demonstrate how Bitswap works, and I'm going to need 2 volunteers. Anyone? I know it's early. 2 volunteers. Yes, sir. Stand up. Sir? Too slow, sir, at the back. Come forward. How do you pronounce your name? Yeah, please stand in. Is it
Akshay.
Akshay? And Akshay and Blake. Thank you very much, Akshay and Blake. Quick round of applause for them for volunteering. Thank you. So, what's going to happen now? Akshay is going to add a file, a cat picture, to his IPFS repo, and this gentleman, Blake, is going to request it. So, Akshay, could you add this to your IPFS repo, please? Through the medium of unwrapping the file. What have you got? Have you got pure data there? You've just got a block. That's incredible. So it's lucky. You hold on to that. It's kind of lucky that this cat picture was chunked into a single block. That was very convenient for the purposes of this demo. But, you know, chunking algorithm, we can set the block size large. And it turns out that when you added it, very curious, but the hash came out as QMcat.
Yeah.
That is a complete coincidence. So you now have a block in your block store. We can say, there you go, there's your block store. And it's got a CID.
Yep.
Very exciting.
QMcat.
You guys, QMcat. You guys are peers connected via the libp2p in a swarm. You've heard about QMcat. You love that picture.
I love that picture.
You want that picture. You want that picture.
I want that now.
All right. Can you send? See this little thing. This is a manifestation of his desire. This is a want list message.
It's kind of underwhelming, actually.
I know.
I have a big desire.
Because
It's
want
very
list
small.
messages are pretty small.
Right.
But what you should do is you should throw that at Akshay. Amazing, Akshay. What does it say on it?
He wants QMcat.
Do you have QMcat?
I think so.
You should totally send it to him. Can you throw QMcat to him?
Yep.
Now, obviously, you still have QMcat because of computers. We didn't have Incredible. Hey, what you got
I'm finally
there?
complete. I feel myself.
Right. So you got some data from the network. How do you know what it is?
It says QMcat.
Oh, amazing. Job done. So we just saw a block get traded. There was a want list and a block came back. A demo almost so trivial that it feels like a bit of a waste of your time. Yeah? Or maybe I left out some key details for the purposes of education. So you received a block from the network, but it didn't come with a CID. Uh-oh. Because would you trust a random stranger on the internet to tell you what a thing was called?
Yes.
You would, I know. You would,
I'm
sure.
very trusted.
You're out.
But do you think we should write software that just trusts data that comes in? No. So what you got from Akshay was a block. It didn't have this big old CID on it. You'll notice the attention to detail here. This CID is on a large card. What you got, what Akshay actually sent to you, let's rewind. So you have a block in your block store with a CID, very cool. When you make your copy of it and send it as a Bitswap blocks message, what you put on it is not the CID, but the recipe by which you can construct the CID. Ooh. Now notice that the recipe is smaller than the CID as well. So A, if I send you a CID, you shouldn't trust it. And B, if you shouldn't trust it, why send it at all? So what you're going to send is data. Oh,
With the recipe.
data with the recipe. Let's go. I'm sending you one list. We can assume that. And you caught it. Now what are you going to do? You've got a recipe and a block.
I gotta do math.
You gotta do math. But what you're going to do is really important math. You're going to use the recipe, which includes the multi-hash header, to tell you which hashing function to use and what hashing function length you're expecting.
I prefer Blake 2.
Sure. That's not what you got. And it isn't what you asked for. Because you asked for a CID, which included the expected hashing function that would have been used.
Right.
So, sorry, bud. Ask Blake 2 next time.
Yeah.
So you're going to hash the incoming data. You're going to discover, by giving the recipe, that it is in fact QMCAT. And then there's one last step that you do, which is, okay, I have independently verified the data that has arrived. I've derived the CID. I didn't trust your CID, no offense. Just got to check. And then there's one more step. You had a want list. You sent it out. So this message got sent. You received it. I mean, the message is dead now. It's been eaten. But in your head, you're still like, I'm still waiting for QMCAT.
Yes, I am.
When's that going to come?
Yeah.
You just hashed this block and it said, it's QMCAT. And you're like, I was waiting for QMCAT. That's totally rad. And then you stick it in your repo, which can be like under your t-shirt. There we go. It's done. Should that have come through with a CID that you weren't expecting, you might have dropped it on the floor. So, as an example, you've got this, I've got this, you've got those, you've got one. I come on the network, and I say, hey guys, let's connect. And I say, hey, can I have QMCAT? And what do you guys do? So I'm like, oh, thanks guys. So I take the recipe, I hash it, I discover it's QMCAT, I look at my want list, I say, yes, finally, I have QMCAT. And then this one comes in, and I'm like, oh my god, recipe, hash it, it's QMCAT. Oh. And so in Bitswap land, that's essentially what happens. If you get a block that you've already received, or basically if it's no longer on your want list, you drop it on the floor. That way, people can't just send you blocks and have you store them. That would be bad. So there's one last theoretical scenario that could happen. What if I send out my want list, but it's for QM dog? Do you have it?
I do not.
Do you have it?
Maybe.
You,
You have to send the request.
Yeah, there you go.
No.
What do I do now? Based on what we talked about 10 minutes ago.
Start walking the DHT.
Yes!
Yeah.
So, in the situation that I throw out my want list to all and sundry, I don't get a response pretty quickly. In the background, I'm going to be like, oh, LibP2P, we got a problem, no one's giving me the thing I want. And LibP2P is going to, don't worry about it, I got this. And then it's going to walk around, it's going to say, you want QMCAT? Okay, I know about QM Calder. QM Calder's going to be like, do you know who can provide this? And Calder's going to be like, no, but I know about QM Kathy. She might know. So then you can, QM Kathy, who can provide this? And she's going to be like, Zach's got this, Zach's got this, Zach's not here, sorry. Theo? Theo's got this. And then Theo, I connect to you, I send you my want list.
Whoa.
And then you send me the block. Ta-da! It's okay. We can imagine this happens. Yes, thank you, Theo. Round of applause for Theo for not dropping his pen. That's great. Sorry.
Don't worry.
All right, that was the Bitswap dance. Hope you're feeling a little fresher. Feel free to ask questions.
So how about just briefly, so what if you actually use a different hashing algorithm? It's the same blocks underneath.
Yeah.
Actually, it's a different formula. So if you, in the end, actually could get QMCAT that's encoded using a different multi-hash.
Yep.
Same block.
So,
No, but would it matter as far as how you chunk it? Would you get a different CID chunk it?
yeah. So that in terms of Bitswap, you're only ever going to, like, the CIDs would have to match perfectly. So in the event, so it would be a strange situation where you sent out a one list for a CID and someone gave you back a differently hashed version of the same thing. But in the event of that happen, you would just, the only thing your node could do is assume that was bad data and drop it.
Right.
and you, as a human with a good brain, you're like, potential optimization. You could have actually found out that that was the same thing, but it would be strange for nodes to be like, you asked for CDX and I gave you CDY, but I happen to know that they're the same.
Yeah, so it only works well when CMCAT is all hashed in the same way.
Yeah.
Using the same hashing algorithm, the same chunking algorithm.
Yeah.
So, and there's default options, I think, with Kademlia.
Yeah.
And as far as to just go with defaults.
Yeah. I didn't go too deeply into the prefixes, but we can see that I can see that there's CID v0, there's DAG PB, which is the multi-codec, and then there's the multi-hash function and hash
That
length.
information is already there in CID, right? Why do you still have to send the recipe?
Very good question. That information is already there. So the question is, if the CID is self-describing, why do we need to send the recipe and not the CID? So essentially, it's because you shouldn't trust the CID. The CID includes the digest, the hash, whereas the recipe doesn't. So in practical terms, the CID is more bytes on the wire than the recipe is. And also the recipient should never trust someone else's output of a hashing function.
Well,
So
why would they trust the recipe that is even sent? If they already know the recipe, why would you even need to send any recipe back?
So because the message, it's not request response. There's no session. You send out. It's just message passing. Right. So I have sent out a message saying I want these things, and then at some point later I start receiving blocks of data.
Right.
So they're not connected. So then I've got a block of data just with a recipe attached. So then the first thing I do is use those parameters to tell me how to hash this data, so that I end up with the CID that I should end up with exactly the same CID that you think you've sent me, and that CID hopefully is exactly the same CID that's on my want list.
And also forces us to verify it rather than trusting
Right,
it, because
so-
there's no CID, there's no way for me to integrate.
Right, so if the spec, because of course this is like, there's multiple language implementations, and if the spec was like, Bitswap messages include the CID, it leaves the room for developers to get like complacent and be like, okay, I'll trust this. And like way back when I started, JS IPFS had a bug that it wasn't checking CIDs against the want list. So 99% of the time, that was fine. You only ever received blocks that you asked for, but a malicious actor could have started just sending blocks to people and then hashing them and being like, cool block, I'll store it. So you saw in the demo, I received 2 blocks that were identical. I stored the first one and then in my head, I took the CID off my want list. So when the same block came in milliseconds later, I was like, well, it's not on my want list. And I don't have to know at that point it's not on my want list because I just received it. As far as that subsystem is concerned, it's like, you're not waiting for this, so drop it on the floor. Go for it.
What kind of like, are there any systems in place to make, like, let's say you send out your want list, to like recall that back? Because if you're like just discarding all the messages that come,
Yes.
you're going to be like wasting a lot of bandwidth.
Yeah.
It's not like insignificant.
So good question. Like if I announce to a bunch of peers I want a thing, and then I get it, and some peers with much higher latency are still sending me things, or I've asked for like hundreds of CIDs and I start getting them. So there's 2 messages in Bitswap. One is want lists, and the other is data. But a want list message also has a flag in it that if you set to like true is basically like a cancel. So you can send a want list or basically a do not want list.
Okay.
So yes.
One more question.
Of course.
So with by sending the recipe back, you're also going to generate the same CID that you wanted.
Hopefully.
And that would also prevent someone sending you like a bad recipe that is actually exploitable where you could cause collisions, because you're going to end up with the same CID that you actually requested.
Yeah.
But then what happens if the content, wouldn't that cause duplication of content where it's got different recipes involved? Like if I use SHA-256 and
Yeah.
I use a different SHA algorithm, even though it's the same content, I'm going to end up with different CIDs. Is there a deduplication for that?
No, and that is a tricky problem because it's one of those things that's like it's quite simple. Like once you understand those primitives, you're like, wait, what if I have the same content and I've used a different hashing function? But that's a difficult problem for IPFS to solve.
Right.
Because we would have to like normalize every hash, or we'd have to do a lot of extra work. Like it's solvable, it's a tractable problem.
Yeah.
But it's more like the system is optimized for like you're speaking the same. So you're speaking the same set of hashes, and if people have got specific reasons to change it. What's interesting is there's a lot of flexibility in the CID. Gives us a huge amount of leverage to upgrade things in the future, but it doesn't mean that if we do upgrade things, all the old stuff is still discoverable by the new CID, which is a problem. But there is a general assumption that you would have to have a good reason to want to start messing with the hashing function, and that you are probably doing something app specific. You're kind of creating your own little island of data that's using the non-standard hashing function.
But later on, you could probably add like some translation table, right?
Right.
Where you realize these two hashing algorithms are popular, so therefore we're going to hash the same item twice.
Yeah. Totally. But it's doable, but so then it's a performance hit because we would have to be essentially normalizing everything, maybe hashing them twice.
Yeah.
But I think so right now a lot of it is stored as particle buffers in exchange, but actually if you use IP LD, you can have aliases.
Right, yeah.
And transferring actually the CID of the IP LD object that actually has links and aliases for the same content.
Yep.
If you do get rid of base encoding, that's actually I think that's one less to hash of them. So it's just
So remembering that this is just a wire protocol that's designed to be implemented by lots of people. So if we were to kind of lump IPLD in with that would become orders of magnitude more complex than it is now. Right now it's super simple. So just for everyone else, yeah. Oh yeah, of course.
So how do you prevent leeches? Like if you have someone requesting blocks but not serving any blocks.
Yeah. I have a slide on that. Currently, we don't prevent leeches. But we could, and with your help, we will. But right now, there's no logic in there to prevent that.
Isn't there like a credit/debt system?
In the paper.
So,
Okay.
and implemented, the Bitswap ledgers exist, and we track send and receive blocks between every peer, but we don't use it for anything other than stats. So, for everyone else, let's just recap. We saw a lovely dance. Thank you to our volunteers. The cast and crew of that performance were the want list, which is this stateful tracked list in memory of a running node, where each peer stores the list of CIDs that they want to get. Then you've got a want list message. This is a snapshot in time of a current statefully managed in-memory list. So the want list message is a snapshot. 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 You get it. My in-memory representation changes, but the snapshot fires out to the network and is listened to by connected peers. And then hopefully you get some blocks messages back. So a blocks message, good shot. Blocks message is a message that contains one or more blocks of data, each one prefixed with the recipe for how to calculate their CIDs.
Sorry, real quick question. I think it should be a pretty easy answer. When you send, your want list doesn't just include a root hash, something that has multiple blocks or chunks, right? You might put in the command get one CID,
Yeah.
and it's going to make a want list for every leaf.
No.
Purple that. No?
No, because it can't. And we will get to that in 1 minute. So just quickly, just to recap on the verification start, I think we covered it pretty detailed, but you send the recipe, you don't send the CID. The recipe includes the CID version, the multi-codec, and the multi-hash. These are all the things you need to calculate the CID. And if you use all the same ones as the person on the other end did, you will end up with the same CID, assuming that the data is correct. So on receiving the blocks, the first thing you do is use the hashing function to hash the data you got. Then you prefix it with the right codec and the right version. CID will match something in your want list if everything is working correctly. If it's not working correctly, and you've either already received it or someone is trying to send you bad data, you drop that data on the floor.
So is the multi-hash binary comparison, so where it's based in encoding that you're using matters?
Is the multi-hash a binary comparison? I don't know. I don't know what.
Are you doing string comparison? Base 32.
Yeah. It's not a string comparison. It's the bytes array format. So in the implementation, CIDs are represented like they're stored as bytes, and then you project them out as the string version. So to your question, I've got a root CID, and I want a whole file. I don't just want. Ta-ding! So the general flow is I want this CID, And eventually you get a block back and you verify it and you store it in your repo, done all that, and then you finally get around to looking at it and you're like, holy crapola, this thing has so many links in it. This isn't a file. This is just like 1,000 links. So then you take, so what's interesting is you send out a want list with one CID on it. Then you're like, okay, bit of a bigger one now. Here's a want list with 1,000 CIDs on it. And then the network will give you back whatever subsets of that it can.
That's automatic, right? When you receive it, when you say get.
If you say get a root CID, you're basically saying get recursively, like get all the way down the tree. So the general flow is, I want this CID. Oh, thanks, another layer of the graph. I want these CIDs. And you repeat, depending on how deep the graph is. Yes, sir?
Yeah, another question. So in the example that you gave, it was one CID that you were throwing out. And that makes sense with the XOR function. How does that work when you're doing multiple at a time?
Right. So in terms of Bitswap, it just means...
Like the seeking. You were looking for CM cat, and that was closer to CM Chandra.
So the DHT thing, right? So there's two subsystems at work. Bitswap is to connect peers. So the first thing I do is ask my connected peers, because they're going to be the fastest responders. Maybe I'm connected to someone who already has this data, and I can send out a want list of any arbitrary size. Great, that bit you understand. So then, if maybe some people can respond with some of the CIDs, but maybe some of them I don't get back. At that point, in parallel, I can do many separate DHT queries. So I can do a DHT query for every single CID.
So is it just interval based? Like how often are you sending out these want lists?
Well, you send one out proactively as soon as you do a get, and then you will periodically refire it. If a new peer joins your swarm, you'll send. If you've got an open want list, you'll send it to them, because there's an important where do these two systems join up?
Yeah.
So the DHT you finally tells you, here is a set of multi-adders and a peer ID. I know this person has told me that they have that CID. You receive the multi-adders at the DHT level. The Kademlia receives them. And then the first thing it does is go, hey, libpeer-to-peer, we've just discovered another peer. Add them to your swarm. So you connect, they're part of your swarm. You've just added a new person to your swarm and you've got an active want list that hasn't been fulfilled yet. So the first thing you do is be like, hey, new peer, got any of these? And of course, so there is this slight kind of brain disconnect there, where the DHT has told us this person has it, but it just kind of by quirk of how you new person connected, I'm going to send them my want list. It's not quite as direct as and go and get the thing from them. It's get in the queue, get as a connected peer, send a want list. You're into Bitswap land. Bitswap does its job. And then because they're now part of your swarm, you've sent out the first CID. You've got back a block that now links to hundreds, but you're still connected to the person who gave you the first one. So he's going to receive your bigger next layer of the graph 1,000 CID want list. Chances are, if they gave you the root, they probably have the whole tree. So they're likely to be the first responder with all the rest.
So then if you don't have if he doesn't have all of those blocks, and you don't have anybody in your swarm that has all of those blocks, do they basically start to help you find other people to pull into your swarm?
I do not believe they do currently, no.
Okay.
They could, they don't. Whoosh! Also, some of the feelings that kind of broadcasting of want lists starts to evoke sounds a little bit spammy to ask everybody about everything all the time. So what's interesting is Bitswap as the definition on the wire, the protocol definition is very simple, just broadcast want lists, receive blocks, but that then frees the application layer up to be as intelligent or as dumb about how it chooses which peers to tell. There's no mandate that says you must tell every peer. You don't have to send your want list to everyone. That would be a simple, naive implementation, which was exactly what we had a year ago. And now we have a thing called Bitswap sessions. Certainly in Go IPFS, JS IPFS is still catching up. But Bitswap sessions is just a way of the application layer tracking some state about which peers it's been speaking to, which peers have been responding well to previous requests. So it starts to optimize. So in the case where you get a root CID from peer A, it means that Bitswap is going to target the next round of want lists for that graph directly to that peer that responded well, instead of sending it out to everyone. But if peer A happened to have just the root block and not the second layer of the graph for some reason, then it would eventually announce to more peers. It was it's very stateful, very kind of trying to do a lot of heuristics. So it's wait, wait a few milliseconds, no, not responding, start to fan those requests out to more peers and more peers and more peers until eventually you get a response. And it also optimizes that list. So it optimizes by peers who've responded successfully, and it then adds another layer of optimization, which is I will prefer peers who are responding quickly. So trying to speed things up. Very big note and an invitation to all of you. Like if you want to make IPFS faster, as you can probably tell by now, if we can make Bitswap more intelligent, if we can make Bitswap work faster, you will literally improve everyone's experience of this peer-to-peer network. Get involved. Like it's active endeavor. Hannah is leading the charge on this. She's working on Go Bitswap, so IPFS/Go Bitswap on GitHub. If you can test out some of the open PRs, that would be amazing. If you can propose new optimizations and kind of unpack how you think that will improve things. With tests would be amazing. People always laugh at with tests. It's a shame. But like if you're looking to help make IPFS faster, this would be a really like high leverage spot to help out on. Any questions about Bitswap?
So what's the, or also with more of the DHT, what's the worst case scenario in regards to distance from your peer ID to the content ID? Like, because there's probably a certain amount of hops in a certain time frame that would be necessary until it times out. Is it possible that even though there's a peer that has the content ID, that it times out before I can get it, before the amount of hops it is that takes it to traverse the DHT?
I'm not, as far as I'm aware, we're pretty pathological that we just keep walking the DHT. The timeout is, if it exists, it's incredibly high.
Yeah.
Adine.
I don't know how you have things set up. I think like it's a chaotic network, right? It's possible you don't find the person who actually is, you did a provider records, you set up provider records in 20 years, and then 19 of them are dead now.
Oh.
The last guy, like his internet is like kind of shaky, like you might just miss it, right? But then he's back again. So you sort of do your best to just look around the network. In theory, if everyone is like perfectly, if everyone can talk to everyone else nicely, then it should be at most like log of the size of the network in terms of how many jumps it takes to get where you're going. Okay. Right. I don't know if that answers.
Yeah, well, it answers the question, does it provide a solution?
Right.
Well, it's a
yeah, it's
chaotic
complicated.
network, right? You're doing the best you can in a non-deterministic network.
But is that something when it's like, in 10 years when most of the world's connected to a stable connection, like say 5G, then, if that pipe dream happens, then would that solve because we've got more stable connections, or is that we're going to run into the same issue?
Stable peers would definitely help.
Yeah. Stable peers make the hops like very like I go to the person who's close, tells me the next one to go who's closer until I eventually get where I'm going.
Yeah. Right. And then someone else in the DHT posted session when we were doing the group, they mentioned like Coral as an alternative to Kademlia, and then how Coral does certain optimizations for the introduction of the neighborhood sharing of overflow. But that seems more when the clients that do have the provision is getting overloaded and they kind of distribute it out. It doesn't seem like it solves the distance towards the content.
Nope.
And there's some like high level principles because again all these things are new. Lots of research to be done that like all of us can sort of think about and help with. And I think probably like two like big trade-offs to think about is the more people I tell some piece of information, the more of you in this room that I tell a piece of information to, the higher likelihood it is that someone can ask one of you and get the piece of information. Right? But that means that if all of us are doing it, then we all have a very high cognitive load of remembering everything. Right. So it's like balancing off telling everyone and also how many people I have to ask to actually get to the right. And it's like latency versus memory for the entire network.
It's a huge tuning and performance problem.
Yeah, right. And those are like the big principles at play. Right?
Yeah.
But if that can be improved, then like that would be such a big gain. Like if we
All right. Let's pause because this is good chat and there will be time at the end.
All right.
Boo boo boo. Grab sync. So if Bitswap is a thing, it's quite contextless in that you send out CIDs, and you get one back, and you're like, oh, I definitely want all the things that this is linked to. If only I could have told you that I want this CID and everything it links to. Right, in Bitswap you can't do that. You're just sending CIDs and getting blocks back. GraphSync is experimental. It's not something that you can really turn on in your IPFS today, but you will hear people talk about it if you listen to the IPFS IRC channels and get involved. So it's worth touching on it very briefly. Where GraphSync hopes to improve on Bitswap is to be able to tell so when you send out a want list, instead of just sending a CID, you can send a CID plus some context. Like you can tell the recipient, I want this CID and everything it links to. So you might pass what we're going to call an IPLD selector. Basically a way of saying, like, can I get CID star? Like, give me everything from here. So that then the remote has more context. It's like, oh, okay, I won't just give you the block. You're probably going to want all of them, so I'm going to start sending you all of them. But it's early days. If that kind of optimization excites you, then GraphSync is the place to go and lend your muscle. Boop, boop, boop. On to pinning. Pinning is how you tell IPFS, please keep these blocks. So to quote Why Are You Sleeping? IPFS makes it feel like every block is local. There is no command to say, go and retrieve this file from a remote server. So pinning is how you tell IPFS to always keep a given block locally. And right at the start, we said when you add a file, it's stored as blocks in your repo. But it is also worth noting that every block you add or you get from other peers is cached in your repo. So if you've got a cache, then you're going to want to manage it. So you can control the cache size by just setting a max size limit in your IPFS config file. And then you can enable garbage collection to ensure that IPFS does its best to keep the amount of storage under that max size limit. So if you store more blocks than your size limit, then the GC process will fire garbage collection, and it will delete all unpinned blocks from your local repo. So we can see that in action in the web demo. Garbage collection, I mean, it's not the most exciting thing in the world, but so I added previously the cat picture. I got these blocks, and I can, so what these currently mean is red is the root block, so it's pinned recursively. We'll go into that in a minute. The green ones are pinned indirectly, because the red one is pinned recursively, they're transitively pinned. And the grey ones are unpinned. Now, what's interesting is these grey ones you can see right now, these are metadata. They're not quite the same as unpinned blocks. This is the pin set. It's a quirk of this demo because this demo is visualizing the output of IPFS refs local, which is like every single block in your repo, including secret metadata that we don't really talk about. It's the pin set. It's how it tracks what is pinned. And it's also the output of IPFS pins ls, which tells us every block that is pinned. So we can unpin, so this is the cat pick. If we were to go and open this one on the gateway, if we were going to open this CID on the gateway, we'd see the cat pick. But this is about pinning. So these things are pinned. So if I run GC now, nothing much happens because there's no unpinned blocks that it can remove. Caveat, like the gray ones are unpinned, but they're the pin set, so it can't remove them. But if we unpin everything, blah, the grayness of cache. Okay, so now they are all unpinned, I can run GC. And as this is what you might, this is the visual model, like unpinned things thrown away. And then just for the sake of it, let's see the cat again.
Those blocks that are left over, are those the pin settings?
So the block, that's still the pin set. So we can see like way more blocks. I think that might take a while. What did I do? 32 bytes. It's going to be so many. It's a terrible idea. Never do a thing that you've not demoed before. All right, we'll come back to him later. Anywho, quick visualization of pinning and unpinning. So let's talk about it. The red one that we saw in that previous slide, in the previous web demo, is pinned recursively. So if you run IPFS pin ls, it's going to list out all the CIDs in your repo that are pinned along with the pin type. So this one is pinned recursive, and these ones are pinned indirect. So you can probably have a guess at what that means now. So the recursively pinned red one is how you say, please pin this block and all the blocks it links to, and all the blocks they link to, and all the blocks they link to, until you run out of font sizes to put on your fancy slide. So and this, hopefully, you got a bit of a mental model of the structure of DAGs and graphs from Core Course A, so that the whole like directed acyclic graph thing. So this is, you have a root block for any given file. Recursively pinned means pin the whole tree. And so that being able to pin something recursively is a useful labor-saving endeavor, because it means you didn't have to manually pin every single transitively referenced block. Just, from your point of view, it's one CID gets me a file. Also of note, like the green ones are pinned indirectly, so they're the ones that were referenced. Also worth noting, IPFS is going to pin files that you add to your repo. So it's a way of like, oh, we assume that you care, like you want to keep files you add, they're your files. But files you get from others are not pinned. So they make it into your repo and they are cached and they're reprovided, but they're not pinned. And so there's an interesting discrepancy there. Like stuff I add is pinned, stuff I get is not pinned, but I can elect to pin it. So why have cached but not pinned blocks in your repo at all? Why bother? Reciprocal co-hosting, as I like to call it, or as came up from a question, like don't be a leech. So if you get blocks from the network, you store it in your repo so that you can be a provider. But it's useful to have this kind of two-level thing. So as with torrents, like you download some bits, you then become someone who can reprovide those bits. So then what we use pinning for is just a way of saying, okay, it's really like a mechanism for managing what to garbage collect and what not to. So so imagine you're running IPFS Companion and you're visiting lots of web pages and you're loading them through the IPFS network. You're then becoming a co-host of those websites. And IPFS kind of opts you into that by default, which is interesting. And I applaud that choice. I think it's good. But eventually you might start to discover that you've visited all of Wikipedia and you maybe don't want to host all of Wikipedia. So then you can either trigger garbage collection manually, or you can just set a max size and let it slowly clear out blocks that you don't want to keep around. And then pinning is a way of saying proactively, actually, I bloody love Wikipedia. I'm going to pin it. And I'm going to store that. I'm going to get a bigger hard drive. And I will also proactively say to IPFS, don't ever garbage collect Wikipedia because I care about it so much, I'm going to preserve a local copy and offer that up to the network and become another provider.
Is there a way for the DHT to know who's a provider that's pinned it?
No.
A provider that's got it potentially ready to go.
So it doesn't differentiate whether it's pinned or not pinned, even if it's in my cache, I'll be a provider.
Exactly. So we don't tell the DHT that level of context. We just tell the DHT we're providing things, which is interesting because obviously if everyone enables GC and you're telling the DHT about stuff that you just happen to have, that could lead to more DHT churn. Might be interesting context to, there's a potential improvement there. But right now, and it also depends on your provider strategy. So by default, you provide things you have pinned and things that you have not pinned. But you could, if you know that you're going to have a very churny cache, that stuff that you don't really want to provide, you could limit your provider strategy to only announce blocks you have pinned. So an important point, the word pinning in IPFS land has become overloaded. It's a slightly confusing term now because of the way that IPFS is transparent about whether blocks are locally stored or remotely stored. So I can use the pinning command as a way of saying I'm going to grab a copy of this remote thing and rehost it, or it can mean I've added this file and I'm pinning it locally. It's the same thing either way. It's a local operation. But some people use it to refer to I will become a co-host of a remote data set. Also, it's overloaded because there are pinning services, and these are people who provide an API that let you ask them, could you pin this for me on my behalf on your local machine? But for the purposes of us who understand IPFS, pinning is local, I pin to my machine. And to help frame that understanding, it's the pin set, right? You saw the gray blocks in the web demo that I kept pointing to as metadata, these ones won't go away. Pinning is local because all you're doing is adding CIDs to this pin set, which is just a list of unique CIDs that you have added, that you have said, IPFS pin this CID. There is an elective course with Hector about cluster, and IPFS cluster is amazing. At some point, you're going to write, like, just as a infrastructural pattern of using IPFS, if you're doing more than just personal experiments, if you're hosting data for other people, you probably don't want to just keep having to get a bigger and bigger hard drive and a bigger and bigger server. You probably want to scale out horizontally. IPFS cluster lets you do that. It lets you shard a pin set, split a pin set across multiple servers. And so it lets you set a replication factor. So if you've got 10 IPFS nodes in your cluster, you can say, give me a replication factor of 3, and then you just add your files to one cluster node, and then cluster under the hood will spread those blocks out across 3 machines. So there's 3 copies at least across 10, and then it will start to load balance. It'll start to balance the data storage. So as you add more and more files, it's going to shuffle around the blocks so that there's always 3 copies, but that each machine is storing roughly the same amount of data. The other cool thing about cluster, that I'm probably going to rob Hector of telling you, but you can make a cluster of clusters. So that's super cool. Just going to leave that out there.
What stage of development is that?
Cluster is so good. It's almost 1.0. Yeah. There's people inside the IPFS team who are like, IPFS should be IPFS and cluster all the time. Cluster is great. All right, the home stretch. Deleting. Oh, I do not want this block. I don't want this block. No, deleting is local. Most important point. We're all fans of peer-to-peer world. This probably won't come as a surprise to you. You can run IPFS blocks RM a CID and remove it from your repo, but you cannot remove blocks from other people's repos because they are individuals with agency. And as they can't delete things from your repo, you cannot delete things from their repo. And you'd be surprised how many people come on the office hours calls and be like, how would I remove something from IPFS? And it's like, well, have you ever sent an email to your boss that you shouldn't have? Right? It's once you send it, it's gone. I mean, notwithstanding corporate Microsoft Exchange servers, but once you send it, it's gone. There's no bring that block back. So if you add a block to your local repo and you don't share it with anyone and you delete it, there's a good chance that's gone. Notwithstanding other people adding it independently, there's no backseas.
Couldn't it be a cool service to then scan the DHT for new blocks to then find out what's interesting and then?
You are paying attention. So the next line in my speaker notes is the difference between IPFS and the current model is if some website publishes something illegal and you ask them to take it down, they can take it down, but there's no way to know if some other website hasn't replicated it, mirrored it. You just cannot know. And in IPFS, you can at least get a subjective view of the network you can see and say, DHT find provs, is anyone still got this? Is anyone providing this thing that I'm very embarrassed about? And you can use that to then frame how you approach the world. Maybe it's gone and you can just not talk about it, or it's still there and you're probably going to have to own up to this now. Shit. But yeah, that's a really interesting difference, and I think that's an improvement that IPFS offers, yeah. It's important to be honest about UX blunders. If you try and do an IPFS block RM on a CID that is pinned, instead of just doing what you meant, currently IPFS will give you an error. It'll say, can't unpin that. I can't delete that because it's pinned. And as someone who cares about UX, I think that's just the thing we have to fix. I think I understand what you meant in that case, and I'll unpin it for you and then delete it. But so good to know right now, if you're going to try and delete something, you may have to run IPFS pin RM first. If you see that error, don't panic. You can delete it. Also, what I discovered with the web demo is don't delete your pin set metadata because your IPFS gets very unhappy very quickly. The IPFS block remove command will do whatever you tell it to do. So there's a couple of pointy edges in that one. Because I was trying to simulate GC and bad things happened. I've deleted a lot of local index DBs getting that demo to run. Do not replicate. So lots of people talk about censorship resistance and that kind of thing, and IPFS is trying to make that possible. But it's also worth noting that like sometimes there's data that you can't replicate for legal reasons or don't want to replicate for ethical reasons. So there are situations where you don't want to participate in the replication of some blocks. This is something that IPFS could do way more to support. So like there's an idea that we could allow individuals, organizations, nations to publish lists of CIDs that shouldn't be replicated, lists of CIDs that you shouldn't attempt to host in order to comply with local laws, beliefs, or social norms. That way, instead of it being a situation whereby, say, you try and access YouTube from the UK and you try and see some video that has like restrictions where it hasn't been released in the UK, and it just says, like, YouTube just makes a guess of where I am accessing the internet from based on a really reasonable estimate of my IP address of access. And then I often see various videos where it's like, you cannot watch this. It's like, what? It's ridiculous. Stupid laws. But more importantly, like, everyone should be empowered to kind of decide what content is good and bad for them, and what we want to get to is a future where you're not denied access from where you happen to be accessing the internet from, but more based on like electing to subscribe to some lists of CIDs where you're then choosing to say, I won't do this, and it's more based on informed consent rather than centralized, like, gonna babysit you, you don't get to look at this. And if you're interested in that topic, we're gonna run a deep dive on it later today. There's lots of challenges there. Like, imagine we convince a nation state to start publishing the list of CIDs they don't want their inhabitants to look at. Those lists could become very long. Or, if you have a small child, like I do, imagine that people start publishing naughty lists of terrible CIDs. They probably shouldn't be stored in plain text where anyone can just go and start like looking at all the CIDs that are on them. Because instead of not hosting them, you're giving like people like children. I'm just sort of reaching, like, if I was a kid and I found a naughty list of CIDs, the first thing I'd do is not apply it. I would look at each CID in turn until I went mad. So it's a challenge, but that's the deep dive. This has been the life cycle of data in the DWeb. Did you have a nice time? Yeah. Woo! You're all qualified IPFS space wizards now. So you know about as much about IPFS as I do. Let's make it better. Could be right.